All right. We had the test yesterday. It did not go as well as it should have for a number of reasons. Number one is I did constructive interference on my solution for destructive interference. So the equation had a 1 where it should have had a 1/2. Well, actually 1/2 where it should have had a 1 for the thin film one. That was one of the two that you knew was going to be on the test. So hopefully people were prepared for that since I told you it was going to be there. The other mistake that I made was it turns out Jeffrey sent me an email about it, the one with the polarizer. It turns out that I did not do the inverse cosine of it. I just did the argument for square root of intensity 2 over intensity 1 and didn't do the inverse cosine. So I had the wrong angle there because I skipped a step. I looked at my notes that I had done. My notes were all right. It was just doing the calculation on the spreadsheet. And so I apologize for this. I know last semester I got dinged for having not the correct solution, which was a new thing and has now recurred maybe too many times. I must be getting old and senile. That's the only solution I have for that. So I apologize for that. At any rate, I will get the test grade as soon as I can, so you get them back. I think the other tests are now actually stapled together and ready to return to you. I realize I haven't given you have access to all of them, of course, on Moodle, but not the actual paper, just the scans of the paper with the grading marks. So I'll give you the actual paper sometime soon, like, I don't know, if you come by my house to pick it up or class period sometime. Of course so.
Do you say what you knew about that question? Or?
No, I did not say. I haven't graded anything yet. Because, I've got to see what people did before I have an idea. Fortunately, I do grade on the process, so that helps. But I can't believe no one asked me about the polarizer one. Okay, let's get to relativity then. Relativity, we've been working, and we were supposed to talk about addition of velocities on Friday. Didn't get there, so we'll start right there. But first, just a reminder question about time dilation. Or is this length contraction? Yeah, no, this is time dilation because it has to do with stopwatch. Suppose Usain Bolt carries his own stopwatch, assuming both his stopwatch and the stopwatch of the official are exactly correct. How do the times compare for Usain to run the 400 meters and for somebody to measure, for him to measure it from the other person? Okay, people who haven't answered. Noah, Brittany, Michaela, Corso. Now it's Noah, Michaela, Corso. And Angelina. Sorry, I missed you.
And that's what I use my picker. I think I looked at
actually, I guess, you can probably use using your data to work. Right. I think the college's network is still down. At least my tablet won't connect. You're connecting? Okay. Maybe it's just my tablet now. Okay, so everyone but Noah who is out to get her phone. So we had 0, 16, 2. All right. 16 people is pretty strong agreement. Those 16 people are thankfully right. Was the last class period where we had no one with the right answer? Usain's measurement will be shorter because when you're doing a relativistic calculation, one of the first things you always need to determine is which reference frame is going to be measuring proper time, and or which reference frame is going to be measuring proper distance, proper length. And proper time is measured in the reference frame that is at rest. Well, Usain Bolt is at rest with respect to himself. So in his reference frame, he's at rest. And the starting and ending points of the race are right here where he is. The starting and ending points are moving, but the events are occurring right at him where he's at rest. Another way of saying this is an object always measures its own proper time. So if Usain Bolt is measuring something about his body, he's measuring proper time for it. And the race is his body that is going from point A to point B. So he's going to measure the proper time. It's really important to be able to do that that identification. With this relativity stuff, the actual calculations are not very demanding. But making sure you have the concept straight, identifying the proper frame, that's where it's demanding. And of course, coming up with the bizarre things. So let's take a simple situation for addition of velocity. So this here is saying that I have Abe and B in their little spacecraft, traveling at relativistic speeds. So let's say like B is traveling at 1/2 the speed of light with respect to A. So that means the speed of B with respect to A is 0.5 c. We would write that as B subscript BA equals 0.5 c. And then let's say B fires off, and we're going to start real simple. She fires off a torpedo cannon, a photon torpedo is what I meant to say. A photon torpedo, what is a photon? We haven't specifically mentioned it yet in class, you probably know. It's the particle for light. So a photon torpedo is a Star Trek way of saying fires a laser weapon. So B fires her laser weapon. How fast is the light going to travel? Speed of light and back. So she fires her photon torpedo. Light goes away from her at at the speed of light. But Abe sees her as traveling at half the speed of light. How fast is he going to see the photon torpedo traveling? Let's start with this in what we do daily. If I am riding in a bus, and the bus is traveling at 20 miles per hour, and I throw a ball forward at 40 miles per hour with respect to the bus, how fast does somebody on the side of the road see the ball travel? Bus is traveling at 20 miles per hour. I throw the ball, so I see it traveling at 40. How fast does somebody outside of us see it traveling? 60. At 60. Because we have the Galilean transformation there. The velocity, in this case, I said ball, so velocity of the ball with respect to, and we'll say Richard rather than bus because that would be V sub BB, it's not very clear. The velocity of the ball with respect to Richard plus the velocity of Richard with respect to the Earth will give me the velocity of the ball with respect to Richard. Oh, I said that wrong. Velocity of the ball with respect to Richard plus the velocity of Richard with respect to the Earth will give me the velocity of the ball with respect to the Earth. You can look at the subscripts and match it out. These inner ones are the same subscript. And the outer ones are the initial, the one we're looking at, and the one that we're doing the comparison to. That's the Galilean transformation. That's how you got 40 miles per hour plus 20 miles per hour is 60 miles per hour. If we applied that to this situation, we would have had the velocity of it has P there, but I said that the photon, let's say photon cannon. The velocity of the photon with respect to B is the speed of light, c. And the velocity of B with respect to A is 1/2 the speed of light. If we use the Galilean transformation, we would have the velocity of the photon with respect to A is c plus half c is 1.5 c. So the light is traveling at 1.5 speed times the speed of light. There's an internal inconsistency in saying that the light is traveling at 1.5 times the speed of light. It's not possible. And so we know that the Galilean transformation can't be correct. Now, if you were Corso or Alex, you would have been in the calculus class yesterday where we actually derived the relativistic equation for adding velocities. It starts the same. Notice the top part of this equation is exactly the same as the Galilean transformation. But we have to divide by an additional term. So let's do this for the case of the photon torpedo. So we're going to say the velocity of the photon with respect to B is equal to 1c. The velocity of B with respect to Abe is equal to 0.5c. So the velocity of the photon torpedo with respect to Abe So there's our calculation using the relativistic equation. Now, if I put my values in, that's going to be equal to c plus 0.5c over 1 plus c times 0.5c over c squared. Those c's on the bottom, 2 c's cancels with 2 c's. And I have 1.5c on top divided by 1.5 on bottom is equal to c. So the speed of light as measured by A is still the speed of light. That's important because we go back to our starting points in relativity. Our starting points in relativity were that the laws of physics are the same in all inertial reference frames, and that the speed of light in vacuum is the same in all reference frames. And so now we have a velocity addition that agrees with that second one I said, that the speed of light in vacuum is the same in all reference frames. Now, of course, if we were only doing the calculation with light, we would just always say the answer is C and move on and never do the calculations. So we do things with, somewhat more realistic. See, here's an example of the calculation with light. Somewhat more realistic numbers. Okay. All of this is just talking about the arrangement. I've said the first and last are these two, and then the middles are the same. And it's the same here, the same two. So it's easy enough to use that equation. What if I wanted to reverse it? If I wanted to know the speed of something measured by B using the measurement from A, well, all I have to do is use those same rules. If I want to find the speed of the photon measured by B, that is speed of the photon measured by A plus the speed of A with respect to B divided by 1 plus speed of photon A, speed AB over C squared. Using the exact same formulation, making sure the inner indices are the same index, and the outer ones match what I'm looking for. There is one difference in these equations, though. I had the speed of speed of B with respect to Abe in the first calculation. I have speed of Abe with respect to B in the second calculation. What's the relationship between those? To put it in a practical sense, that's like saying I am moving toward Arlene at a speed of 1 meter per second, as measured by Arlene. But as measured by me, what's happening? I'm stationary. What's Arlene doing? She's moving toward me. That's the opposite direction. It's still going to be 1 meter per second. The separation between us is decreased by 1 meter per second, but opposite direction. So anytime you flip the order of those indices, you have to change the sign because the direction changed. And so that value of VAB is minus VBA. And so when we do the calculation in the reverse direction, we would have, the velocity of the photon with respect to A, that's C. The velocity of A with respect to B is minus 0.5 C. So I'd have 1 minus 0.5 on top, or 1/2 C on top. And on the bottom, I would have 1 plus C times minus 0.5 C over C squared. Again, 1 minus 0.5 on bottom. 0.5 over 0.5 gives us 1 again. So it works the same in reverse, but you have to keep in mind the directionality for the velocity. And so that's what all of this is talking about. You see, that's what this equation comes from. So solving these problems, I've said it many times until I get hoarse. Make sure that you have the middle index is the same and that the outer indices are the ones you're looking for. Excuse me. Now let's do a problem that's not trivial. 2 spaceships travel at high speed in the same direction. So I have, here's spaceship A. Here's spaceship B. Same direction. As measured by an observer on a nearby planet, ship 1 is behind ship 2, so A is 1, B is 2, and moves at a speed of 0.90 C. So the speed of A with respect to observer is 0.90 C. Ship 2 moves at speed of B with respect to observer is equal to 0.70 C. So just to make sure we're clear, we have an observer down here who sees those 2 speeds of the ships. Says, well, ship A is overtaking ship B because it's traveling 0.2 C faster. The question is, according to observer on board ship A, how fast and what direction is ship 2 moving? So let's start with the easy thing. What is somebody on ship A going to say for the direction ship B is moving? It's going toward them, right? Because the separation between them is getting smaller. And ship A says, I'm hanging out here. I'm doing nothing, just watching the world float by, and that ship's coming toward me. Now we need to determine how fast is it coming toward us. What would I have said if I was a Galilean thinker? The person on the planet says the difference in speed is 0.2 C. So how fast would I have said that it's coming toward me? I would have said 0.2 C. But we now know it's not so simple. So we have to go through and do the calculation. So what is the answer I'm looking for? Speed of what with respect to what? The speed of 2, which I called here B, with respect to 1, which I called A. So that's what we're looking for. And now using our formulation, I left off the indices. What can you tell me about the indices? Okay, let's start with something simple. What should the first index be right here? Okay, you said 2? Yeah, it should be B. How do I know it's B? Because the first one here was B, so that one has to be B. And likewise, this one here is the same as that. What is the second index going to be for the second velocity? A. Because the second one, let me change colors to make things clear. The second one needs to be the second one here. What about the index in between the two? Okay, observer. They have to be the same. It doesn't matter what they are as long as they're the same. But the observer is the only other index we have. And so the one in between is going to be observer. Now I have my indices in. I look at my values. VB0 we have 0.70C. VBO. VOA we don't have. What do we have? We have VAO. So how do we go from VAO to VOA? Reverse it, which means change the sign. Now we have all the numbers we need, and we can put in our calculation. So that's 0.70C plus negative 0.90C all over 1 plus 0.70C minus 0.90C over C squared. Cancel where we can, so these two C's cancel with that C squared. And we are left with 7 times 9 is 63. 1 minus 0.63 is 0.37. So we put 20 over 37. Minus 0.54 repeating. Of course, we only have 2 sig figs, so 0.54 is the correct answer. C. So it's not 0.2 C that A sees B coming toward him at. He sees as more than half the speed of light. Question?
Really fast. Will you be able to sync this up with us?
Yes, once the internet is up and running. And maybe it's right for you, but I couldn't connect with the tablet. So once it is connected, then yes.
Thank you.
So, an example of how to use addition of velocities. Pretty simple to do, but you've got to have the, how do you get those indices straight? Or you can't do it. So here's pictures showing everything. We've done it. Next clicker question. Which really, a spaceship traveling, you can answer now. Okay, Alex and Erika are the only ones that have answers in. A spaceship traveling at half the speed of light as measured by Earth fires a photon torpedo at the speed of light. How fast does the photon torpedo travel as measured by Earth? Are you able to connect now? She doesn't know if she's able to connect. And yeah, she's answered so. Brittany and Corso. You tried? Well, while we were waiting for Corso, 2 people changed their answer. And where we are now is 4752. Turn to the person next to you and ask them if they've been listening to what I've been saying. Okay, let's try again and see if you found somebody who had been listening. Spam the button, Corso, maybe it'll work. Did I? It's still on. Well, while Corso's trying, I'll leave it here for. Corso's in! Yay! So after reconsideration, most of you found somebody who had been listening. So Erika, tell us.
Well, I see what the correct one would be. I would be because
Oh, no.
I was saying if the torpedo is shot forward, like it'd go faster, but then it'd go this way, the other way to the back, it would kill the ship. But it would also it would go different directions, so it would have to counteract the speed going this way and this way, wouldn't it?
If it was something going slower than the speed of light, then it would depend on the direction you shot it. But if it's something going the speed of light,
It doesn't matter.
if it's light, in other words, something goes speed of light, the speed of light is the same in all reference frames. You don't even need a calculation for that. Because it's light, it's going to be the speed of light. And so going through the relativistic calculation, remember, I said that I gave you this example exactly with half the speed of light and the speed of light. And we worked it out going forward and backwards. We worked it out both directions, saw it's the speed of light in both cases. And then I said, and if it was the speed of light, we would never do the calculation. It would be trivial. We would just rely on that postulate of relativity. The speed of light and vacuum is the same in all reference frames. And then we went to looking at examples where, an example problem we did, where it's not the same. So it would depend only if it was not traveling at the speed of light, if it was not light. This one here could never, ever occur. Nothing can go faster than the speed of light. The first time through, before 2 people flipped their answers at the very end, we had 7 people at half the speed and 5 people at 1 times the speed, and I was really distressed. So it got better. Now on to Doppler shift. When you think about the Doppler shift, what is it you think about? Sound. You think about the action, right?
Yeah.
The Doppler shift occurs in sound for 2 reasons. One is that you have the speed of the object with respect to the medium it's traveling through, and one is you have the speed of the observer. With light, the medium doesn't matter. And so the equation is going to have to turn out to be different. Our textbook only talks about one Doppler shift. By the way, I should mention the velocity addition equation we did is only for parallel. Only if the velocity is parallel or anti-parallel to the speed, the velocity difference between the reference frames. If you have a perpendicular component to velocity, it's a different equation that we did not do. Our textbook pretends that there's no Doppler shift if you had something going around you in a circle. If it's not getting closer or farther, it pretends there's no Doppler shift. That is perfectly true with sound waves. There is no Doppler shift if something's not getting closer to you or farther from you. It's only the relative change in distance from you that matters. But with relativity, there is a Doppler shift if something's moving transverse. So you might have had and it might come up again, a reading quiz question that asks about the Doppler shift when the probe is passing at its nearest point. And the answer they want is 0. But it's not the correct answer. So you know the answer is 0 because that's what they want. Why is that not correct? Why is there a Doppler shift? That is, there is a frequency difference between the frequency emitted by the ship and the frequency you receive if it's going around in a circle, never getting closer or farther. The answer is something you can answer. We call it, by the way, the transverse Doppler effect. Okay, maybe I should back up. What is frequency? The number of, not wavelengths.
It's how long it takes to repeat.
The wavelength is how far it takes to repeat. That's the period. The period is how long. Okay, frequency is how often. It's the number of repeats per unit time. Now, if the spaceship is traveling around me, what is changed for my measurement compared to the ship's measurement that we've already learned? The measurement of time. We have time dilation. So if I look at the clock on the ship, that clock on the ship, let's say that it ticks once a second according to the ship. According to me, time is dilated. I'm going to measure a longer time between the ticks. Even if it's going around me in a circle, I'm going to measure a longer time between the ticks. Which means that I'm going to have the frequency with which I measure the ticks is lower. So there's a Doppler shift for relativistic effects, even if it's not moving toward you or away from you. So we're not going to look at the equation for that, but I just want you to know that there's a little bit of a problem there with the textbook ignores it, and then that reading quiz question pretends it doesn't exist. This here is the equation for the relativistic Doppler shift for parallel motion. Notice I was clear here for parallel motion. If something is moving toward you, you're going to have it shift to a higher frequency. So notice in this equation, if the object is positive, the frequency is going to be higher. So if something's coming toward you, the object is higher. So this is measuring positive velocity if something's coming toward you. This is really important in science. Why? Because we look at stars, and it turns out all those stars are moving with respect to us. And if they're coming toward us, we're going to be a shift toward higher frequencies. What color has higher frequency in the visible spectrum? Violet. We usually say blue, even though violet is the technically correct answer. And so we say that there's a blue shift if it's coming toward us because the colors are all shifted toward the blue. If it's moving away from us, what color is at the low frequency end of the visible spectrum? Red. So if it's moving away from us, we see a red shift. Now, Edwin Hubble, famous for the Hubble Space Telescope today, but the Hubble Space Telescope is named after him because he observed that when you look at things out there, stars, the farther away the star is, the bigger its redshift. The redshift, how much the frequency is shifted toward the red, which translates directly into how fast it's moving away from us. So Edwin Hubble observed that stars that are farther away from us move away from us faster. Stars that are closer are not moving away as fast. Which then, it's very easy to say that must mean that the universe is expanding, that things are moving away. And that gives us a big change in our understanding of cosmology by observation of that Doppler effect. So that's, using this equation, just remember the object is positive if approaching. And that would give you a blue shift. So approaching, blue shift, positive V object. Going away from you, red shift, negative V object. Now to stuff that, well, I find it even more fun. Momentum. Up to today, momentum had the equation, momentum is mass times velocity. Now we're changing this. Now we're saying momentum is gamma times mass times velocity, where gamma is that 1 over square root of 1 minus v squared over c squared. When I was your age, when I was taking this class, we learned that mass increases as something moves faster. That is now not the way it's taught. I now accept it. And so mass is always constant. When I was in school, they just said the rest mass. Now we should say mass is constant. No matter what reference frame you're in, you have the same mass. So if I am traveling towards you at half the speed of light, you're going to see me as thinner. But if you make a measurement of my mass, which you can't have me stand on a scale and do, but there are other interactions you could do, you would find the same mass formula. The reason we had it two different ways was that factor of gamma can be used to just define something else. So the mass of things is constant in all reference frames. No change in mass, but the momentum is no longer mass times velocity, it's gamma times mv. Now, here I have u written instead of v. The reason for u is so we don't get the speed difference in the reference frames confused with the speed of the object we're looking at. Because in this equation, you're inherently saying, I have a ball in reference frame B, and I want to say, what's its momentum as measured in reference frame A? And so I have the speed of reference frame B with respect to A is what we call V, and then the speed of the ball with respect to reference frame A or B, whichever one we're in, is the U. So U is just the speed of the object we're looking at. V is the speed of the reference frame we're looking at. And this gamma is going to be the speed of the object, gamma. So let's look at some things and see how this works. First of all, this equation here is Newton's second law. The true form of Newton's second law is that the net force is equal to the derivative of momentum with respect to time. That's the true form. And that's got to be true because we said the laws of physics are the same in all reference frames. So if that's one of our laws, that's Newton's second law, it's got to be true. But since gamma is now a function of time, then you can't replace dp dt with mass times acceleration. So this equation is not true in a relativistic case. The sum of the forces is mass times acceleration was true if you didn't have a change in mass and if it's non-relativistic. But the fundamental Newton's second law equation is true in all reference frames. So in relativity calculations, we have to use this relationship. I'm sorry. I was getting better. Let's do a problem then. If Newton's second law is correct, then we should still have conservation of momentum in a collision. So here is a collision. A proton has a head-on collision with a nitrogen. This is how carbon-14 is made in the atmosphere. Except for the carbon-14 is, actually, it's a neutron has collision with a nitrogen, actually, my mistake. Neutron has collision with a nitrogen, becomes a nitrogen-15, the nitrogen-15 is unstable, it kicks off a proton and becomes carbon-14. That's how carbon-14 is created. Okay, but let's just do this problem. We have a proton strikes with 0.70 C, it recoils with 0.63 C. So we have a picture here showing the before and after. That nitrogen was initially at rest. For conservation momentum, the nitrogen is going to have a momentum going off this way. How do I use conservation momentum? What have we always done in the past for conservation momentum? Go ahead. Somebody was answering. Okay, some of the forces external is 0 was a requirement for momentum to be conserved. And then we said momentum initial is equal to momentum final, right? And they're vectors, but this is all in one dimension, so I don't have to put the vector sign. So what's my momentum initial here? It's what? Well, that's the velocity. Remember, that was too far. Remember, momentum relativistically is gamma mv. So what would it be? In general form, it'd be momentum of the proton 1, right? Which is gamma proton 1 mass v proton 1. That's what we start with for momentum. What is gamma proton 1? Gamma proton 1 is equal to, and I should have put mass of proton there, 1 over the square root of 1 minus v proton 1 squared over c squared. So that's momentum of the proton initially. Now we can calculate this as a number. I usually like to keep my variables all the way through, not so much in relativity. I like to go to numbers in relativity. So let's calculate what gamma proton 1 is. 0.70 C. Okay, so C divided by C squared divided by C squared, those are going to cancel. 0.7 squared is 0.49. 1 minus 0.49 is 0.51. And then we have to do that in the old calculator. That'll help. What do we get? $1.400. So that's what the gamma P1 is. And we could go further than the mass of the proton. We're going to make life easy. We're going to say the mass of the proton is 1 and the mass of the nitrogen is 14. So we're going to put mass of the proton is equal to 1. It's 1 atomic mass unit, right? And so we can do this. That's going to be 1.400 times 1 atomic mass unit times 0.70 C. 7 times 14, 49 times 2, 9. I assume that I can do that math in my head. Anyone want to doubt me? Okay. So that's our initial momentum. What's our final momentum? I have that plus, and what does it ask for, just to make sure it says what's the speed? Yeah. Plus the momentum of the nitrogen so I have those two things. So I need to calculate those. Gamma proton in the second case is going to be 1 over the square root of 1 minus 0.63. I'm not going to put the C's redundantly. 1.2877. Minus 0.63 C. Why did I put a minus there? Opposite direction, right? You have to pay attention to the directions. So multiplying that through so setting these equal, bring this across. And 9 and 8 is 17. Finally, it's divided both sides by 14. Oh, brother. I said finally before we do the hard work. So I have 0.1279 C is equal to the gamma of the nitrogen times V of the nitrogen. One question that you ask yourself is, do I have to worry about gamma? Is gamma going to be significantly different from 1? Because I have 0.128 roughly C, if gamma was 1, my speed would have to be 0.128, which means that I would be about 3% off with my gamma as 1. So the answer is no, I should not assume gamma is 1. I'm going to have to go ahead and calculate correctly. So now I have to take this right-hand side and expand it out. Well, let's do it long form because I'll confuse myself. I wrote it like that because now I have V in only one place. So now I square both sides, swap things, and I have that relationship, add the 1 over c squared, and at this point, I would just go ahead and calculate what 1 over 0.1279 squared is. So let's do that. So that's 61, right? And so add 1 to that. Take the square root and do the inverse. And we get VNC is equal to 0.1269 C. So boom, we're able to calculate it. Was that quick and easy? You bet it wasn't. But we were able to do it. I guess we'll talk about rest energy and whatnot. Finish this up on Friday.